So we've talked yet, right now we have a screening test, we have a cutoff value, and we get our 2x2 table, and then we can work through what are the relationships among these things. But here's a question. How do we decide what the cutoff value should be? How do we determine what the number should be if we're doing a screening or diagnostic test? So here we have a dimension. This dimension is A1C. Along this dimension, we have two frequency distributions. A distribution of people without diabetes on the left, distribution with diabetes on the right. Higher A1C, more likely diabetes, as you know. What cutoff value should I use, A through E, in order to get perfect sensitivity, optimum sensitivity? Now, you only get to choose one letter. I say with a smile. You can't choose two answers. I want to get best sensitivity. So, somebody, person's giving me the number, that's perfectly fine. I want to get best sensitivity. Well, that answer would be, of course, B as in boy. Not D, B. Because from the B line over to the right, I have absolutely all the people that are diabetic, right? Please note, if I were to choose D, I'd only have half the diabetics to one side and half the other side. That would be terrible sensitivity. B is optimum sensitivity. But wait a minute. When I use B, I'm bringing in all of these healthy people at the same time. Right. Who cares? Who cares? Because all we're concerned about for sensitivity is, did I get all of the disease people? Well, did I get all the disease people? Absolutely, yes, I did. Therefore, perfect sensitivity at B. All right, you know what's next. Which cutoff would give me optimum specificity? Which cutoff value will give me optimum specificity? Some of you are already anticipating this. Right, that would be D. D as in dog. Why? Because from that D line, now looking over to the left, I have all of the healthy people, every single one. Oh, and by the way, the fact that I brought in a bunch of disease people by mistake is irrelevant, because it's not about being right overall, it's about getting all the healthy people identified. I have all the healthy people identified. Everybody to the left of the D line, excuse me, all the healthy people to the left of the D line. I've identified correctly all the healthy people. Well, you know what's next. Let's talk predictive value, shall we? Which cutoff should I pick to have optimum positive predictive value? Which cutoff line should I pick to get optimum positive predictive value? What is positive predictive value? It's when everyone I said has the disease actually has it. Optimum positive predictive value, well, that would be D, as in dog, optimum positive predictive value. Because from the D line over, everyone I say has a disease has it. And B, be optimum negative predictive value. Because from B over to the left, I have nothing but healthy people. I wouldn't pick C. C is not as good as D. Because I pick C, although at D, 100% of the people I pick have diabetes. At D, I have these people that are wrong, so I'm less than 100% for positive predictive value, right? Optimum positive predictive value has to be D as in dog. Because why? Because everybody to the right of that D line is a diseased person, 100%. Everyone to the left of the B line is a healthy, non-diseased person, 100%. Remember, optimum positive predictive value says, give me nothing but diseased people. Optimum negative predictive value says, give me nothing but healthy people. Now let's look at these in relationship to each other. Sensitivity says, give me all the diseased people. And by the way, you bring in a bunch of healthy people, I don't care. Whereas positive predictive value says, I want only healthy people. I said that wrong. I want only diseased people. And if you miss a bunch of diseased people, I don't care. Please note, as I'm showing you this, sensitivity and positive predictive value are very different. Sensitivity says, get me all of the disease. Positive predictive value says get me only disease. Do that again. All disease, only disease. All disease, only disease. Sensitivity, positive predictive value. In the same vein, specificity says get me all of the healthy people, whereas negative predictive value says bring me nothing but the healthy people. Positive predictive value is part of sensitivity, I guess, but that's a really dangerous way to think about this. I want you to think about how they're different. Positive predictive value says, I'm willing to have you miss a bunch of disease in order to bring me nothing but healthy. Sensitivity says, I'm willing to have you bring in a whole bunch of healthy people as long as you bring me all the disease. I want you to notice those are two really different things here, are they not? Sensitivity, all disease. Positive predictive value, only disease. Now, people do tend to confuse sensitivity and positive predictive value, but I want you to notice by this conversation, these are very different things. When I want to make sure I get everybody's disease, sensitivity. When I want to make sure I only have disease people, positive predictive value. Which one of these am I focusing on if I want to be, listen to the words, sure about my diagnosis? Which one of these do I want to pick if I want to be sure about my diagnosis? Positive predictive value. Why can't I pick C for specificity? You can, it's just not as good. Let's go back here. Why can't you pick C for specificity? You can, it's just not as good. If I pick C, well, now can we agree you've missed these healthy people down here in the bottom, right? In D, you've included them. In C, you've missed them. Clearly, if I want to make sure I get all the healthy people, D would be better, right? You could pick C if you want. It's just not as good. D at the tail end, let's do it this way. It's not the center of the distribution, it's the tail end of the distribution that is what's important here. Why is D best for specificity? Because once I go below the D point, I have no more healthy people. Why is B the best for sensitivity? Because once I go below the B point, I have no more disease people. It's not the center of the distribution, it's the end of the distribution that determines sensitivity, specificity, and indeed positive, negative predictive value. Let me go back to where I was before. Now, I want you to notice the idea that sensitivity and positive predictive value related is absolutely not correct. In fact, they're kind of antithetical to each other. As sensitivity goes up, positive predictive value goes down, and vice versa. Because as I change my cutoff score, moving it this way from B to D, my sensitivity is declining while my positive predictive value is increasing, right? As I move my cutoff score from D to B, well, then I find my sensitivity increasing, but I find my positive predictive value going down. Changing the cutoff score means positive predictive and sensitivity are moving in inverse directions. The connection between the pre and the post-test probabilities is not based on, let me try to get rid of that. Come on, there we go. Is not based on sensitivity goes with positive predictive value. No, but the relationship is right here. Sensitivity goes with negative predictive value. Specificity goes with positive predictive value. Can I repeat what I said? Yes. As I change my cutoff value from B to D, then my sensitivity is going down, but my positive predictive value is going up. As I change my cutoff score from D to B, then my sensitivity is going up, but my positive predictive value is going down. Right there, you're talking about the tension of medical practice. Let's take a moment and actually talk about this. So now, let's talk about one remaining thing, and then I'll bring this to a close. Let's look at this just in terms of the formulae. Some people incorrectly think sensitivity is linked to positive predictive value because they share the true positives. They think that specificity is linked to negative predictive value because they share the true negatives. Right, but you're missing the key thing in epidemiology. It's always about the denominator. In every ratio, the denominator is the leverage number. Just look here at sensitivity with me for a moment. Suppose I want to have the best possible sensitivity. How do I get there? Well, that's easy. Pump up the true positives, right? Make the true positives as high as possible, and I'll have the best sensitivity. Yeah, no. Take the true positives to infinity. To infinity. Let me have one false negative, and you'll never be perfect. The way to get perfect is not to increase the truths, it's to eliminate the falses. Once I take the false negatives here and I take them to 0, my sensitivity goes to perfection. At that exact same moment, so does my negative predictive value. And once I take my false positives to 0, my specificity goes to perfection, right? At the exact same moment, so does my positive predictive value. N with N and P with P. And by formula, it's all about the denominator. All right, humor me now. Humor me. Without looking at the screen before you, what kind of falses are in the denominator for sensitivity? That's easy. False negatives. What kind of falses are in the denominator for specificity? That's easy. False positives. Why is that easy? N with N and P with P. If I want to have the best possible sensitivity, I want to reduce my false negatives, N with N. If I want the best possible specificity, I want to reduce my false positives, P with P.